Alright, so let's recall that in the previous calculus video we defined the notions of average velocity and instantaneous velocity of an object that is moving along a straight line, which is a coordinate line. It's not simply a straight line but a straight line on which there are real numbers. These real numbers help us know the positions of the object at different instants of time, and that's how we can track its motion. And this type of motion along a straight line is called rectilinear motion. Now let us see an example of this type of motion. And this is the example 2 in the book. It shows the motion of a car along a straight line. The car model is some 1994 Ford Mustang Cobra. The model is not really that important, but we want to see how it's moving and what's going on. So this is the distance versus time graph of such a car's motion. The time is measured along the x-axis in seconds and the distance is measured along the y-axis in meters. So initially when the car started moving, at that instant when t is 0 second, it did so slowly of course, but then it started moving more and more rapidly, and that's why the graph looks like this. Now this is what we have to say about its motion. Say we focus on the time interval between the time instants 5 second and 15 second, this 10-second interval. In that interval, the average velocity of the car is some 35.5 meter per second or 128 kilometer per hour. So let us simply recall what this average velocity was. Say we are looking at a rectilinear motion that is happening along this coordinate line. There are real numbers on this line. And say at the time instant t, the position of the object is s. So it is this point which corresponds to the real number s. Then in some time interval between t and t plus delta t, the average velocity of the object is v average equal to f of t plus delta t minus f of t divided by delta t. Okay. So in our example, t is 5. Delta t is 10. So this is what we have. Now, what is this geometrically? You may remember that this is nothing but the slope of a secant line of this curve. This is the point t equal to 5. When t is 5, then f of 5 is the y coordinate of this point t. Okay. And when t is 15, that means when t is 5 plus 10, f of 5 plus 10 or f of 15 is the y coordinate of q. So difference between these y coordinates divided by difference between the x coordinates, which is 10, is the slope of this secant line pq. So the average velocity, which of course is this quantity numerically, is also related to the geometry of this graph as the slope of this secant line pq. And then the velocity at the instant t equal to 5 second is some 20 meter per second or 72 kilometer per hour. This is the instantaneous velocity, velocity at the instant t equal to 5, which geometrically equals the slope of the tangent to this graph at P. Why? Well, we already know why, but let us also see. So that instantaneous velocity is the limit of that ratio. As the interval over which we consider the average velocity itself shrinks as delta t becomes smaller and smaller. These two ends become nearer and nearer, and if this difference quotient of two differences reaches some real number, then that limit is defined to be the instantaneous velocity. But this is what is it geometrically? Geometrically, it is the limit of the slopes of these secants as you keep P fixed but let Q come towards P. Essentially, what that means is that you are considering a smaller and smaller interval whose right end is coming towards the fixed left end, which is t equal to 5. And then that limit is, of course, the slope of this tangent. That is the instantaneous velocity. All right. So that's what we have here. Now, let us also note something else. Do you recall that towards the end of the last calculus video, I was stressing on this fact that velocity may be negative? That's because we don't really know. I mean, we of course know that the rectilinear motion happens along this line, parallel to this line, or on the line itself. But the direction of motion can change, and it can keep on changing. Like, for example, you think of a simple harmonic motion. Say there is a mean position about which an object is vibrating. So it's going like this, again coming back and going to that direction, and then again coming back. So it's going back and forth like this. In that case, what happens is that this numerator keeps on changing sign. Or even if you do not think of such a motion, you can think of something else like this. Say an object goes some distance from a position and then again comes back. So in one half of the motion, this numerator, which we know as displacement, is positive. And in the other half of the motion, where the distance from its initial position is decreasing, this difference becomes negative. So in one half, the average velocity is positive, in the other half, the average velocity is negative. The same will also happen to instantaneous velocity, because it's just a limit of such quantities. And that is why when you draw graphs of such a motion, distance versus time graph, it may look like this. Okay, it may look like this. The motion may be like this, or it may also look like this. But however these two graphs are, at any instant, what is the instantaneous velocity geometrically? It is the slope of the tangent to the graph at that point. Now, when studying straight lines and their slopes, we saw way back when we were studying these things that lines tilted like this have positive slopes. Here also, if you look at the tangent to that upper curve at this point, then it is somewhat, it has quite a steep slope. As opposed to that, if you think of a tangent at this point, its slope is not that much. But all these slopes, whether they are large or small, are positive because they are tilted like this, not like this. Why? That's because if this is your distance versus time graph of some kind of motion, then as time increases, distance increases. It increases less and less rapidly for the upper curve and increases more and more rapidly for the lower curve, but that is something else. It is increasing, that's what the thing is. And these slopes are all positive, but these slopes are the instantaneous velocities of these motions at those instants of time. So here v, or your ds dt, is positive. As opposed to this, if you consider a motion in which S is decreasing with time, say you are looking at something which is coming towards you, so you are measuring the distance of that moving object from yourself, say. So with time, that distance is decreasing, but in this type of motion it's increasing. Okay, so that's why velocity is positive, here velocity is negative, and the distance versus time graph of that type of motion can be like this or like this. In the lower type of graph, what happens is that as that object is in this type of graph, as the object is coming towards you, the rate at which it is coming itself slows down. Okay, so that's why it's like this. Initially it was having high velocity, say at this instant of time, it was really coming like a madman towards you. But then as it came quite near you, it slowed down. The slope of this line, which is the instantaneous velocity at that instant, is quite high numerically. Okay, its absolute value is quite high. But this one is not that much. Okay, it came down. As opposed to this, in the above type of motion, where also distance is decreasing, initially the velocity was numerically not that much, but as it came towards you more and more, it kept picking up speed more and more. It's like an object that is falling towards earth from some height. Initially it just falls a little, but then as it comes down, its speed increases and increases and increases. So it is that type of motion. But in all of these types of motion, distance is decreasing, velocity, it may be high or low, but all these velocities are negative. So here they are negative. Now let us think of a real life situation. Say you are making a journey in your car to your friend's house, which is somewhat far away. So you, throughout your journey, your speed is 30 km per hour, just saying. Okay, so it's constantly 30 km per hour. Now, if you make that journey, meet with your friend, chat for some time, and then come back. And during your return journey also, the speed is 30 km per hour. Now, if this 30 km per hour speed is being measured from your house, then when you are going towards your friend's house, the velocity should be positive because distance is increasing. But when you are coming back, the velocity is negative. So it is actually minus third kilometer per hour. But the speedometer doesn't show minus. The speedometer only shows the numerical value of your velocity or its absolute value, and that is speed. That is why this device is called speedometer, not velocity meter. So that's how we come to the notion of speed. Speed is the absolute value of velocity. That is, speed is this. Speed has the same unit as velocity, distance per time, in whatever units they themselves are being measured, kilometer per hour or meter per second or miles per hour. Now, let us also see another example, example 3, and with this we are going to end. Example 3 is again the motion of a point moving on a coordinate line, and this time, instead of looking at its distance versus time graph, let's look at its velocity versus time graph. And let us try to understand from this graph what type of motion this object is having. Again, motion is along a straight line. When you see things like this now, suddenly you may get confused. You may think that the object is moving along this curve. No. The object is always moving along a straight line. We are only considering that type of motion. This is something else. Okay, this is the velocity values plotted versus time. Velocity is measured in whatever unit, per second of course, but meter, kilometer, we don't really know. And it's not really given, and that does not matter. So what is happening here? Let's see. So the object, of course, started moving when t is 0 second. At 0 second, at that instant, 0 second, there was no motion. Just after that instant, the object started moving. So its velocity kept on increasing like this, and it reached a maximum value. So during this first second of its motion, it is going away from that point from where we are measuring this distance or that position. Okay, from the origin of the s-axis, it is going away. And then for the second, it is still going away, but now it has a constant value of velocity. That means it's steadily moving. Now its velocity is not increasing. But then from the instant t equal to 2 seconds, the velocity started decreasing. You see, velocity started decreasing doesn't mean the object is coming towards us. No, the object is still going away from us. Even in this third second between t equal to 2 and t equal to 3, the object is still going away from us, but it is doing so less and less, with less and less velocity. But at the instant t equal to 3 seconds, its velocity became 0. So there the object momentarily stopped. It's something like this. It initially started moving, it picked up speed, then it moved with that speed for this time duration. but then it again slowed down and stopped at t equal to 3 seconds. And then velocity became negative. That means this time it's really started coming towards us. Initially it started coming towards us somewhat slowly, but then it really picked up speed. Okay, and at this instant t equal to 4, this motion persisted and it reached its maximum velocity during its coming back, during that phase of motion at this instant t equal to 4. And then again the velocity started going down, but still between t equal to 4 and t equal to 5 it is still coming towards us. Why? Because velocity is still negative. And at t equal to 5 it again stopped. Okay, after coming this much, at t equal to 5 seconds it stopped, and then the velocity between t equal to 5 and t equal to 6 is 0. That means the object is not moving. So it took rest for 1 second, then again it started going back with higher and higher velocity in this time interval between 6 and 7 seconds. That's how we have to interpret this graph. Sometimes what happens now, due to some reasons, we have to consider distance versus time graph, velocity versus time graph, or something else versus something else graph. So we should not confuse among these things. We should really carefully interpret what we are looking at. Otherwise, there will be too much confusion. But now we understand what type of motion this is having, and still it is a rectilinear motion. So you can see that here the object changed its direction of motion. During the first 3 seconds, it's going away. We can call it forward motion. During this 2 second interval between t equal to 3 and t equal to 5, it's having backwards motion. During this interval 5 to 6, there is no motion, and again forward motion in the interval 6 to 7. Now, here also one can think of tangents to this curve. We can think of tangents. For example, one can think of the slope this curve has at this point, at this instant. And this is the rate, instantaneous rate at which velocity is changing with respect to time. It will be the slope of the tangent to this curve at that point. And that slope is your acceleration, how rapidly the velocity is changing. And you can see that the slope of this curve is quite high at this point. I mean, the slope of the tangent, same thing, is quite high at this point, but negative, because it's tilted like this, not like this. And that's because it's coming towards us. So acceleration at this point is negative, but it's high acceleration. At this instant, the tangent, for example, is horizontal, having zero slope. So at that instant, there is no acceleration. And then the acceleration itself changes direction. We will see more about this other rate, the subsequent rate of change, that is acceleration, in the next video. Because acceleration also similarly has to be understood with the help of examples. There are 2 more, and the examples will stop being just simply some diagrams and start being more mathematical, in the sense that we have to calculate many things. And you will see very interestingly, some very complicated motions can also be analyzed, and you can say many things about these motions from these quantities. speed, velocity, acceleration, and even displacement. Okay, so we will see more about these things in the other videos which will come next. So that's just it for tonight, and tomorrow is Saturday. So as usual we have linear algebra. There are more problems to solve. So that's it. See you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.